Hey everyone, so this is part 2 of 2 for buffers. We're still in chapter 9. We're going to talk about buffer capacity and just do some more examples using buffer equation like the HH equation. All right, let's get started. What happens when you react a strong base or a strong acid with a weak conjugate or a weak species? Well, what happens is it's going to react completely. What that means is that if you have, for example, a weak base and you react that with a strong acid, that reaction is going to go completely to its protonated form. In other words, there's not going to be any weak base left, and there's not going to be any floating around proton ions left, because it's all going to turn into BH+. The same argument goes for if you were reacting a strong base with a weak acid conjugate. So again, when you react a strong acid with a weak base, that reaction is going to go to completion, which means, again, that there will be no B or H+ at all, because it all goes to BH+. If you were to write the equilibrium expression or the Ka expression of the weak acid, how would we write it? We would write it normally before, we would write it as products over reactants, which would mean that it would be B times H+ is divided by BH+. Okay, that's how we have seen it before, because a weak acid equilibrium expression means that it starts as the HA basically and it disassociates. But notice what they did here. Instead of saying it as the HA and the A-, they've switched it on you, which means that the BH+ is your HA, okay? So don't get too confused about that. The new K is basically 1 over Ka. Why the heck did they not include the other parts? So for example, remember from your original knowledge, Ka, again, would have been B times H+ divided by BH+. What happened to the B and the H+? That should be on the top of this reaction, of this fraction right here, but it's not. But remember what I said. This reaction goes to completion. So there is no B and there is no H+ left. So there is no concentration of those species. That's why they've removed it. They've basically deleted it from the K expression because there's none left. Everything has been turned into BH+. What is the take-home message of this slide? Is that when you react a strong something with a weak something, that reaction is going to go to completion. So how can you find the equilibrium expression of something for a reaction like that? You would take the inverse of the Ka. So in essence, your K equation or your K equilibrium expression for this reaction would be 1 over Ka of that protonated form, that BH+. So for example, if B is tris is that buffer, that commonly used buffer that we talked about in the previous video. If B is tris, then the equilibrium constant for the reaction with a strong acid like HCl would be, you take the inverse of your Ka. Remember, they told us that the pKa of tris was 8.07. As a matter of fact, it's right here. That's what I had shown you before in the previous video. But the pKa is 8.07. So how did they get 8.51 times 10 to the negative 9th? Well, you raised it. I mean, this is the Ka, right? So they took 8.07 negative and raised it to the power of 10. And that's how they got 8.51. So they would basically divide that by 1, or 1 over 8.51 times 10 to the negative 9, and they get that number, 1.2 times 10 to the 8th. Look how large that number is, okay? That right there tells you that the equilibrium is, that reaction goes to completion. That's a verification. There is no weak base left. There is no strong acid left. Everything is turned into that BH+ because of that huge equilibrium constant value. So now that we know what happens when we add a strong acid or a strong base to something that's weak, let's try to do a little problem. If we add 12 mils of a 1 molar HCl, strong acid, to the solution in the preceding example, being the tris that we had done in the previous video, what will this new pH be? And remember that the concentrations that we had found for the tris hydrochloride and the tris were right here. For BH plus, it was 0.0296, and for the B was 0.1026. So conceptually, if you add 12 mils of a strong acid, everything's going to go to BH plus. It's going to react completely. Okay, so how do we find out what the new pH is? Let's set up our little table. Initially, we have the concentration of the weak base conjugate, which is 0.1026, and we have how many moles of the HCl? Well, we did 12 milliliters times a 1 molar. That'll give you 0.0120 moles of HCl. How much do we have of the BH plus, of the conjugate acid? We figured that out in the other example. So that's initially. Finally, what happens? Well, what you started out with your weak base, your 0.1026, that's not going to be there anymore because you've added 0.012 moles of HCl. So it's going to react completely. So you have to subtract what you added from the strong acid there. So it would be 0.1026 minus 0.012. What you're left with is 0.0906. What happens to the BH plus? Well, obviously everything's going there, right? So you have to add how many moles of HCl you added. You have to add it to that BH plus because there's going to be more BH plus at the end of this reaction. So 0.0296 plus 0.012 is 0.0416. So now to find the new pH, you just plug it into the HH equation. It's pKa, which is 8.07, that hasn't changed, that was given to us, plus the log of these two new numbers. The moles of B, the new moles of B is 0.0906 divided by the new moles of BH plus. Multiply, add, divide all that out, you'll see that you get 8.41. Look at that number. I mean, the pH really doesn't change, right? We added 12 mils of a super strong acid, and the pH only changed from 8.61. 8.61 was the pH that we had obtained in the previous video, to 8.41. I mean, it's not that much. It resists the change. I mean, this buffer works because it resists the change of a strong acid, because everything that you added, every part of that strong acid that you added was consumed and turned into something else. So that's why buffers work. They resist the changes of pHs when you add certain things to them. Of course, to a point, right? If you keep adding acid, that buffer's not going to work anymore because all of your B is going to be consumed, and you have no more for it to react with it. So obviously your pH is going to spike up or spike down depending on what you're adding. That, of course, is called buffer capacity. The buffer capacity measures how well a solution actually resists changes in pH when acid or base is added. The greater the buffer capacity, the less the pH changes, obviously. Now, I'm going to show you a graph that is actually on page 197 of your book. And it's this graph right here on the bottom right, but I'm going to say some things about it first, and then I'm coming back to this slide. So, buffer capacity, this is something that you need to remember because it'll help you maybe throughout some problems that you do. Buffer capacity is at its maximum when the pH is equal to the pKa. Remember that. The graph that I just showed you that we're going to go back to shows calculated response of a buffer to small additions of either acid or a strong acid or a strong base. The buffer in this example is a mixture of HA plus its conjugate base with a pKa or with a Ka of 10 to the negative 5, which would mean that it has a pKa of 5. The relative quantities of the weak acid and the weak base conjugate were varied to give initial pH values from 3.4 to 6.6. And they went ahead and graphed that. That's what you saw there. But then they went ahead and added 0.01 moles of either a strong acid or a strong base. And they wanted to find out how the new pH changed when they added this strong acid or strong base. So, as an example, let's say you're mixing 0.0383 moles of a conjugate base and 0.9617 moles of its conjugate acid, and that gives you an initial pH of 3.6. And we know that because we plugged all those values into our typical HH equation. And we know that the pKa was 5 because they told us that the Ka was 10 to the negative 5. Okay, what happens when you add 0.01 moles of a strong base to that mixture? The concentrations and the pH obviously are going to change, and we know how to do that now. We set up a little table like we did in the previous example, and what do we put initially? Well, initially, the moles of HA were 0.9617. How much are you adding of that strong base? Well, you're going to add 0.010 moles. So that's what you put there. And then it's going to your A minus. It's going to the conjugate base. And how much did we start with though? The conjugate base, we started with 0.0383. Okay, that's initially. Final. Now we know that everything is going to go to completion here because you're adding a strong base to this. So it's going to definitely react. So we know that whatever HA you started with, which was the 0.9617, you're going to have to subtract what you added because it's not going to be as much HA anymore. It's going to all convert into the conjugate base. So you would take 0.9617 minus 0.010, that gives you 0.9517. And then obviously you don't have any more strong base left. Everything's going to be consumed. So only thing you have left to calculate is your conjugate base. You started out with 0.0383 and you know that you're adding the strong base. It's all going to turn into A minus, so you add it to this number. So you started with 0.0383 and you added 0.010. That gives you a total of 0.0483 at the end of the reaction. You plug those two new numbers into your HH equation, and that equals pH is equal to pKa, which we know is 5, plus the log of 0.0483, that's your moles of A minus, divided by 0.9517, that's your moles of HA. You calculate, divide all that out, multiply all that out, and obviously you would get 3.705. So that's your new pH. When you added 0.010 moles of a strong base, it's a change of 0.105. And that value is actually plotted on the top half of this graph. The bottom part of that graph is the same. If you were starting with the same solution or same mixture, it's just you were treating it with a strong acid instead of a strong base. And look at the change. The change would actually be negative 0.136 pH change. So instead of it being 3.6, it would be 3.6 minus 1.136. So what's the take-home message here? Number one, magnitude of the pH change is smallest when the initial pH is equal to pKa for the buffer. Notice something here. Notice the middle of the graph, either on the top half or the bottom half. What's the spot or the area that changes the least? Well, it's around the middle, right? And that's where the pKa is equal to 5. What is the pH of that? It would be around 5. So that's what this is saying. The buffer capacity of any buffer is greatest when pH is equal to pKa. That is something that I said 2 slides ago. It shows you graphically, it shows you visually why that is. There's not much change, plus or minus 1 pH unit around the middle. But obviously, once that buffer has reached its capacity, then the thing starts spiking up or down depending on what you're adding. So when you choose a buffer in real life, right? When you choose a buffer, you should choose one whose pKa is as close as possible to the desired pH. A useful note to remember is that the useful pH range of a buffer is more or less the pKa plus or 1 pH unit. If you notice here, the area where it kind of stabilizes is where the pH is 5 and it goes up to about, 5.5, and it goes down to about 4.5. So it's about more or less 1 pH unit. This is a table on page 199. It shows the structures and pKa values of some common buffers. No, you do not need to memorize these, obviously, but it would be nice if you just take a gander at this table, because obviously I will probably use one of these on your exam. So just, kind of take a look at these and make sure that you understand what's going on here. All right, so that's it for this video, and that's it for buffers as well. I am going to pick up your next video with acid-base titrations. All right, guys, see you later.